Let's consider the effect of differing mass distributions on how easy it is for things to accelerate. Let's consider a father pushing a playground merry-go-round with a force at the edge. So here's my merry-go-round. We exert some force at the edge. We know the moment of inertia of this. If we say we can consider it as a uniform disk with negligible friction, we can say the moment of inertia is 1/2 mr squared. We look that up in a table. We can plug in values and get a moment of inertia. Lovely. Then we want to know what's the angular acceleration when no one's on the merry-go-round. For this, we'll use Newton's second law. Sums of the torques are equal to I alpha. Sums of the torques here are we have one force that's acting on a lever arm R with an angle theta between them. So we can say that's RF sine theta is equal to I alpha. We solve for alpha because that's what we want to know, and we get alpha is equal to RF sine theta over I. Looking at this, since we're pushing normal or perpendicular to that lever arm, we have a sine of 90 degrees. We plug in the 1.5 meters worth of radius, the 250 newtons worth of force, the sine of 90 degrees, and the moment of inertia that we previously calculated to get a calculation for our angular acceleration of 6.67 radians per second squared. That's part A. For part B now, what about if somebody's sitting on this merry-go-round? We have an 18 kilogram child 1.25 meters away from the center. Most of this will be the same. The difference is now our moment of inertia is different. So we'll have an additional moment of inertia from the child that's mr squared with 18 kilograms and 1.25 meters as the mass and distance away from the rotational axis, which means that when we calculate a moment of inertia for the child, we have 28.13 kilogram meter squared. We can find our total moment of inertia by adding on the moment of inertia of the original disk plus now the moment of inertia of the child sitting on the disk to get a total moment of inertia equal to the combination of the 56 from before to the 28 newly found, resulting in 84.38 kilogram meter squared. We find alpha as before, where it's equal to my torque over that new moment of inertia, which then lets us say that we have a new angular acceleration of 4.44 radians per second squared. This is interesting. By adding on some mass, we've reduced the angular acceleration. You might expect this because adding on mass increases the moment of inertia, and that makes it harder to start spinning. It also makes it harder to stop spinning. There you go.